All right, we're good. All right, it's time to get started, right? So today's talk is gonna be on the cohomology of spectra, where we basically define like how to do homology on a spectra. And let's actually start. Our motivation starts from just ordinary cohomology, right? Like singular stuff, basically, right? In like the homotopy of like CW complexes category, right? And these are just these, right? Now, we know why these are special, right? And actually we know that they're actually representable, right? Due to Brown representability, we know that the cohomology groups are actually representable by what we call the Eilenberg-MacLane spaces, right? So like the ordinary cohomology, all of these are representable functors, which is great, right? That makes stuff so much easier. However, can we say the same about extraordinary cohomology theories like K theory or whatever? So the answer to that is you need to move beyond just like CW complexes. In fact, the correct answer to that is you need to move to spectra. Like this is precisely why we want to work with spectra, right? So, what do I mean by this? So let's actually do a computation to see what I mean by this. So, okay, by the way, this slide completely broke in the overleaf, which is why I had to do some manual corrections here, but it's fine, right? So, we're going to start with a computation here. So I want to compute the degree negative n maps in like the spectra category between the suspension spectrum of X and this spectrum HG. What's HG? Probably should have defined this here, but HG is like, so HGN is just the nth Eilenberg-MacLane space. And you guys might know, but there's this like isomorphism, if you will, between KG and the loop space of KGN plus one. And basically we just identify KGN plus one with this loop, KGN with this loop space. So, the characteristic maps are basically just gonna be identity, right? So that's my HG spectra, right? So now if you guys remember from a previous talk, this is one way we can write the maps between like a suspension spectrum and a spectrum, right? And now I want to compute this whole thing. Now I'm going to actually invite someone to like just tell me what the next step should be. What do you guys think we should do next? Any ideas? Anyone? All right, so what we do next is, well, obviously just unwind it, right? Write HGN as like R. So that should be an R. That's my bad. That should be an R. Right, so write it like this. But then, we know that the suspension has an adjoint in the loop space functor, right? So write it like this. But now using this thing I just said here, where taking the loop space basically decreases this, I get this, right? So, but remember that maps between X and Eilenberg-MacLane space is quite simply just the cohomology, and it's the same limit. So the entire thing ends up just being cohomology, right? So what's the upshot of this entire computation? The upshot is that while I can represent cohomology in the CW complex category, I can actually also represent it in the spectra category, right? So yeah, this is my thing. Now it turns out that for a general cohomology theory, including extraordinary ones, we can actually write we can actually represent them also in the spectra category in the same manner, right? So that's kind of the motivation for why we want to define cohomology on spectra, because really it's just a natural extension of how we define it for like how we define the extraordinary cohomology, right? And it just stands to reason, like there's no reason this only needs to be a suspension spectrum. Why not make it everything, right? Allow it to be everything. And we have So this is like the natural definition of cohomology then. And it turns out that the dual to this, the homology, is this thing where you take the mass from the sphere to like the wedge. This is a bit more it's a bit more complicated to derive for like singular homology, right? So just take my word for that for now. And here's an example. So you take K theory, and it turns out that this is representable, and it's representable by this spectrum we call the BU spectrum, which is an omega spectrum, which is like it basically it's like an alternating kind of spectrum, like it's BUU BUU for like the groups, or say for like the space, right? I'm sure like the actual K theory talk will have more details on this, but just an example, right? Right, so now let's talk about some of the properties of the homology we defined. And remember, and again, I'm gonna quickly remind you guys that like, E star, so quickly gonna remind ENX is just the maps from X to E of degree negative N, right? So that's cohomology. And by the way, from now on, whenever I say cohomology, just assume that a dual result for homology also holds, right? I'm not gonna like tell you cohomology and homology both times, unless I specify otherwise. Just assume that if I'm talking homology or cohomology, the dual result also holds, right? So, okay, the first one is that, this is a functor and it goes to graded abelian groups. Well, this is obvious, right? Obviously, this is a functor, and we know that it takes values and we know that this takes value in graded abelian groups, right? The next one is that it takes co-fiber sequences to exact sequences. And here the co-fiber sequence can be in this argument, or it can also be in like this argument, right? And this is also kind of obvious, right? So for the first part, so right, for cohomology, it's obvious. For homology, you have to make a bit of a argument, and that's basically that you have that like wedge product there, and I believe in like the wedge, the smash product, right? And I believe in the smash product chapter, you also had like co-fiber sequences go to like co-fiber sequences or something. So that's like the extra step you have to do there. But otherwise, it's just the same, because we know how those we know how the hom functors basically send the co-fiber to exact sequences, right? The next one we have is that suspending increases dimension by 1, or decreases dimension by 1, if you will, right? So this thing, we'll actually see this a bit more explicitly later on when we're constructing the long exact sequence of homology, right? And then the next thing is we define these things called the coefficient group of my theory, and it's basically finding the homology / cohomology of the sphere spectrum, right? And also, wait, let me actually make a comment. Why is this pi and E? So for example, this guy, this is quite simply the maps from S to E negative N, right? And that's, or say positive N, because 2 negatives cancel out. And this is obviously pi and E, right? And same for this guy, this is the maps from S and then S wedge E, or S smash E. And we know how the smash product works. Like S is the unit of the smash, so it also turns into this, right? So same reasoning. So it turns out that pi and E is like kind of the coefficients that quote unquote determine my homology theory, right? And the last property is that you can do this, like it's in a sense commutative. And this follows from commutativity of smash product. Now, this was actually quite a substantial result when it was originally proved by Whitehead. But we have already done the hard work of proving that the smash product is commutative in the last talk, right? So we actually don't need to do much work. It just follows from the commutativity of smash for us. All right, so now we're kind of gonna go ahead and show that like this like representable functor I defined on spectra when we kind of restrict to CW complexes, that this is indeed like a cohomology theory in the sense of Eilenberg-Steenrod, right? So, recall that if I have a cohomology theory on spectra, then I can restrict that to a cohomology theory on CW complexes by simply looking at the suspension spectrum of the CW complex and applying the cohomology theory to that, right? Now, how do we define relative cohomology? Oh, this is a bit of cheating, but we just define it as this, right? As like the cohomology of X mod A motivated by excision. And this is kind of cheating because we basically get excision for almost free here, right? And so first things first, homotopy invariance, that's just obvious, right? Like homotopy invariance, it makes an isomorphism of suspension spectra, and then and then cohomology is functorial on spectra. So there's that. So now excision, like I kind of told you guys that excision is for free, and let's just write it out, right? So remember, excision means that if you have like the cohomology of X and V, and then U and V cover X. Sorry, I realize I did this the wrong direction. So it should be like, there should be like an intersection right here, right? Yeah. So remember, so if you take like the cohomology of X and V, that's the same thing as taking the cohomology of U and U intersection V, right? That's like excision. Now, basically, how do you get this? You take this isomorphism between, U quotiented by U intersection V being the same as U union V quotiented out by V, right? And then you use homotopy invariance to get this, right? That they have the same cohomology. And then remember that, I defined relative homology to be the quotient, right? To be the homology of the quotient, rather. So we get this, but we said that U and V cover X, so U union V is just X, and we get this result. Now this should be like an X disjoint union point, by the way, right? And the last thing is like, when we're dealing with like the empty set, we say that the quotient is a X union a point, also called X plus in atoms, right? So, excision we basically just got for free. This was just writing out the details, but we literally just defined relative homology groups based on excision, right? So now let's get to the hard part, right? So we're going to prove the long exact sequence of cohomology holds. So first, let's say I have a pair of CW complexes, then I can write the inclusion, right? And as you guys know, from an inclusion, we can write down the cofiber sequence, right? Where X includes into Y, then Y includes into its mapping cone, which is also equivalent to the quotient, right? And then we have this nice extension of it where we can go into the suspensions now, and then this keeps going on forever, right? So this is like the big cofiber sequence. And this is like this is like the general technique with which we'll prove exactness of sequences for like our spectra cohomology theories, because we have already seen that cohomology sends exact sequences like this to like, or say sends cofiber sequences like this to exact sequences. So yeah, apply cohomology to this, and we get this. So first just look at the upper row, right? That's like what happens when you just literally apply it, right? Remembering that the quotient sends it, remembering that the cohomology of the quotient is quite simply the relative cohomology, right? And now basically what you do is you do a nice trick where like suspending decreases the degree of the cohomology by 1, right? And that basically allows you to go down to this guy, right? And we'll actually try to make this boundary map more explicit, but this actually gives us the long exact sequence as promised. So yeah, let's make it explicit now. So, we take that. So basically, what's the only hard part of this? It's this homeomorphism, or say it's this isomorphism, right? Between like the nth homology of the suspension and the n-1 homology of my space. So, what I do is I take the sphere spectrum and map it to the S1 spectrum. And what's the S1? The sphere spectrum is just like S0, S1, blah blah blah, right? And with the obvious characteristic maps, and the S1 spectrum, it's like S1, S2, blah blah blah, right? And the degree one map is just like it's just the obvious map, right? Where you send S1 to S1, S2 to S2, but you have to shift it by one, and the degree is one, and it's component-wise identity, right? So now you can actually induce a map of on the smash, right? So remember, the sphere spectrum is the unit for the smash, right? So I can write that X is a sphere spectrum smashed with X, and now I can use sigma to move it to S1 smash X, right? And this is like an equivalence because sigma up here was an equivalence, and this induces my desired isomorphism here. Right. And basically, like when you're doing the explicit, basically, Adams doesn't really end up using it down here in this chapter, but he says that this is like a nice formulation of the boundary map, and it will come in handy for ever using it explicitly. But just like ordinary homology, like we usually don't really think about the boundary map explicitly. We just use the exact sequence, right? I realize I forgot to add the pause button on this. It's fine. Right, so we're going to define the triple cohomology. So, right, this is like quite similar. So what you do is like, this is like the cohomology of a triple. Or this is the exact sequence of a triple. Well, it's not an exact sequence yet, but basically combine all the information we have so far and add this like boundary map delta, right, where delta is this composition, right, where xy first goes into y by the boundary map defined before, and then it goes into y comma z, like this, right? Now, I want to show that this is an exact sequence, right? And the way I do that is show that it's equivalent to a different exact sequence. So what I do is I take another cofiber sequence, and this cofiber sequence is, so it's this. So it's like y mod z, x mod z, and then if you quotient those guys out, it's x mod y, and then, the suspensions thereof. And as we saw before, it induces an exact sequence like this. And if we show that this partial map is the same thing as this delta map, we're done, right? So, well, by the way, I'll pause for questions now because I realize I'm halfway through my talk. So any questions so far? Anything you guys would like elaboration or more details on? All right, let's continue. Right, so we have this exact sequence, and I want to prove that like this del is the same thing as this partial, right? And the way I do that is through this diagram. So let me explain how we can use this diagram to prove that, right? So if we recall what this del came from, it's like, decrease the page size a bit. So it's like en xy mapped to the suspension of this thing, right? Because that, like, if we directly apply it, that's what happens. And then we identify this with this thing, right? So that's how we did it in like the original long exact sequence. So what we do here, so now notice what happened, like, notice that this part up here is induced precisely by this part of the diagram, right? So what I can do is let me write down an arrow, right? Like once we apply the E functor to all of this, right? Imagine I apply the E functor to everything in this diagram, right? Then I would have an arrow here, which is, and then I would have E n minus 1 y mod z, right? So like this thing would be here because this line is this line. And I can do the same thing for x and y, right? To get to this thing, or rather to this thing, right? To get E and Y up here, right? And then I have that inclusion map J. And basically what this diagram is telling me basically what this diagram is telling me is like, if I go through here, is the same thing as if I go through here. And, this is basically the statement that this composition, which is going through the downstairs route, is the same thing as just doing this, which is the same thing as going through the upstairs route, because that's how we constructed del, right? Or partial. So that kind of proves that these two guys are the same, and hence that proves that this exact sequence, or this sequence I wrote down upstairs, is actually an exact sequence. So any questions on that? I know that was a bit more technical than most the rest of the talk. All right, let's move on. Right, and also it turns out that you can like combine this like double and triple diagrams to get this like bigger diagram. Adams doesn't really end up using it, but I thought it was cool. And this also comes from like a co-fiber diagram, and that co-fiber diagram is called the Verdier's axiom, which is also pretty cool. All right, so the next thing we're going to prove is Meyer-Vittori's, right? And basically, so there's like a clever technique here. So basically, again, anytime we try to prove an exact sequence, you always start with a co-fiber sequence. That's the motto. But this time we have to be a bit clever. So, we know that Meyer-Vittori's is usually about like, U included into V, into like the co-product of them, into like the union of them, right? That's kind of like what Meyer-Vittori's in a vanilla case comes from. But you have to be a bit clever. And the cleverness is the suspension. Why did we suspend everything? The answer is because of this negative I2. Because if you guys recall, in the actual Meyer-Vittori's, like when you pass down to homology, you need that negative so that it turns out to be an exact sequence. And what does negative I2 mean for like including in a coproduct of topological spaces? It doesn't mean anything. However, for suspensions, it does mean something. Why? Because what's the suspension? It's this double cone, right? This is like double cone thing. And I have like two ways to include this into itself, let's say, right? One of them is just like a vanilla identity map. But another one is I can flip it over and then include it. And that gives me a sense of reversing the orientations, or a negative, if you will, right? So that's why we have passed to suspensions to do this. So we take this sequence, and this is just an ordinary co-fiber sequence. You take this inclusion, as I said, right? And then you form the mapping cone, and then you keep doing this. As you guys have noticed, this mapping cone is looking very gross, but it turns out that this mapping cone is actually just homotopy equivalent to the suspension of U union V, right? Why? Well, let's reason this out by diagrams. So
wait,
yes,
before you continue, what exactly is like, can you scroll up for a moment?
yes.
What are we taking the co-fibered sequence of exactly? Is it U cap V into U wedge with V into U union with V, or
No, so we're taking the co-fiber sequence of this inclusion right here, right? And right, so let me actually tell. Actually, it'll be more clear when we look at the drawings I have down here, right? So let's look at that. So basically, yeah, so you have like the you have like the suspension of U intersection V, right? And this obviously includes into the suspension of, so this is like the suspension of U intersection V. This is the suspension of U wedge V. So this should be wedge, this should be an intersection, right? And basically, you obviously have an inclusion of this guy into this guy. How? How you just like, so let me in the right color. So, I'm doing I1 minus I2. And what does that mean? That means that first I put this guy into V, right? So with the normal orientation. So I put this into V. But then I also put this into U, right? And or say into V. And then this is like a negative orientation. That's kind of what's happening. And yeah, like I want to look at the mapping cone of this map, right? So that wasn't the best explanation. So, but like that's basically the idea, is that I want like this two different orientations on the two ends, and I'm like putting this guy back in this guy. That's all that's happening. So now we make the mapping cone of this guy, right? And imagine that U and V are basically organized in a way like this, right? This is U, this is V, and the purple is the intersection of them, right? So when I put that in, it becomes this nice intersection. And now I make the mapping cone of that map. And I have like two perspectives of the diagram. They're not very well drawn, but yeah. So one of them's like, you basically put them in the way I described, and you have like, the end of the cone in the back, right? Another way you can look at it is like you put the two suspensions down, and then you insert your U intersection V like this, and and then look at the cone upstairs, right? Now, like the basic thing here is that once we have looked at the cone, right, notice that the backbone of this cone forms this cylinder, right? And basically what we can do is we can deform along this cylinder, so that we can identify this part and this part. And what basically ends up happening is that we have like U wedge V, and we're ending up identifying their supposed intersection, right? So all it becomes is like U union V, and obviously the suspension of that, because we still have the double cone stuff, right? So that's kind of the rough reasoning as to why we can turn this guy into just this guy, right? And now we put this in, and we have a much nicer looking co-fiber sequence, right? And this actually looks exactly like Meyer-Vittori's, right? So you just apply the homology functor now, and there you go. You have Meyer-Vittori's sequence, right? And
Okay, thank you.
yeah. And basically it turns out that you don't actually need like the input to be a CW complex. You can, or the suspension spectrum of a CW complex. You can, this actually holds for like every spectra basically. And we make this thing called the Meyer-Vittori's co-fibering, where if you have a CW spectrum, which is the union of subspectra like this, then you can basically form kind of the exact same co-fiber sequence that I put up above. And you might be thinking, why don't I have suspension here like I had above? And the answer is that, as you guys might know, every spectrum is actually a suspension, right? So that's why we don't actually need to do this. We automatically have that these guys are suspensions, right? So yeah, that's all I wanted to mention here, just that you can generalize the co-fibering to this. Right, and this ends this part of the talk, and I'll be going into spectral sequences next. But before that, do we have any questions? All right, let's move on. Right. So now that we have like kind of seen how to do cohomology of spectra, right? There's some nice tools to kind of compute them, from what I understand, and these are called spectral sequences, right? Like the idea of a spectral sequence is like, you basically like take finer and finer approximations of your homology theory, and it turns out after a finite number of steps you have perfectly approximated it, basically, right? And let's actually formally define what spectral sequences are. So we're going to do it for homology. There's you can also define it for cohomology, where you kind of change the degrees a bit, but Adams does it mostly with homology, so I'm going to do it there. So basically, formally, it's something like, it's like a collection of objects like this for each pq in z squared. So it's a collection of objects like this, and then it's a collection of maps dr, where dr is a map that has degree negative r minus 1, right, or by degree negative r minus 1. And we call it a differential because it satisfies this dr squared equals 0 condition, right? And so here's like or actually, let me put the next axiom in, and then I'll explain the kind of the visual intuition behind this, right? So we also want that we can increase the r by taking the homology of er with respect to dr, and what that actually means is like you take the kernel of dr going from er pq, and then the image of dr going into er pq, and mod them out, right? And okay, let me explain the visual intuition behind this. So this is kind of ripped out of Hatcher, the explanation I'm about to give to you. So if you guys want to read that for maybe a more complete picture. So basically the idea is like this. So basically the idea is that you have a collection of pages. Right? You have a collection of pages. I actually used black. So you have a collection of pages, right? On my first page, I've like this grid, like this z squared grid on each page. But on my first page, all my arrows are, decreasing p by 1 and not decreasing q at all, because r equals 1, right? So it's my r equals 1 page. On my first page, everything's just, moving to the left, right? These are all my arrows, my differentials. And basically, to get to the next page, you want to know the value of at the next page of this point. You compute the homology of this point with respect to like this and that, right? So you mod out by the image of this and the kernel of that. So you move on to the next page, right? And basically you get to the next page by computing all the homologies, right? I've moved on to the next page. And this time the differentials are a bit different. They're going a bit farther now, right? And I've gone to the r equals 2 page, and then I keep doing this. And after a finite amount of, for each point after a finite amount of time, ideally you'd have come to a page where this approximation is actually exactly equal to the homology you're looking for, right? So that's like very roughly the idea. At each step you're taking this like finer and finer approximation, right? And yeah, that's kind of the point of like spectral sequences. It's like you're moving up pages, and each time you're like getting closer to the homology by getting rid of like some stuff that you don't need, right? So that's the idea of spectral sequences, very roughly. Now, right now, let's talk about convergence of spectral sequence, and this is going to be a bit rough, right? So we're not going to go into the exact details. So basically, like we say that we say a spectral sequence converges to a graded abelian group like this, and we notate it like this. If for each pq there is some r, so that dr is basically constant after a while. I guess it should be r naught. I think I messed up the order here. It should be like this. Yeah. So yeah, like it's constant after a while. So basically after a while you cannot get better approximations because you're done, basically, right? And then the next one is kind of a technical condition, but it's basically saying that and we don't need to worry about the exact details. It's basically saying that with this approximation you can basically get to like the nth homogeneous part of A, right? Like basically it's like, or close to it, let's say, right? But that's what it means to like converge to my spectral, for my spectral sequence to converge to this like graded abelian group. So now let's talk about the Atiyah Hirzebruch spectral sequence. Pretty sure I mispronounced the last name. So, it's
I think that was
the
pretty good, actually.
Oh,
That's at least how I've been pronouncing it.
all right, Hirzebruch, we're gonna go with it. So, there's this like spectral sequence such that, this is like the terms on some page, and that spectral sequence converges to, fp plus q of x, right? So, like basically, if you take cohomology, or if you take homology with coefficients in the homotopy of f, then like that makes like a spectral sequence that allows you to approximate your homology theory. So let's actually look at the details of this, because we still have to define those differential maps, right? So to do this, we use, and I think for most spectral sequences, you start with some kind of filtration of your space, right? Something like this, or all of these are like subcomplexes. And the next thing you do is like you take all possible combinations of like pairs and triples of this and put them in like some giant interlocking diagram, right? And like this, and Adam says that like the spectral sequence is like, the correct route through this like giant maze, right? So that's how the spectral sequence is how you kind of distill out the exact information you need. So, we're actually gonna so there's like two ways Adams gives us to construct this spectral sequence, and there's this way we can do it called the using an exact couple. And I'm gonna use that today because I've seen that being used for other spectral sequences also, so I think it's more useful, right? So let's actually let's start this. So you have this like obvious diagram, right, where you include xp minus 1 into xp, right? You include this pair into this pair, and then this is just a connecting homomorphism, right? And now what we do is we sum up over all the p's, right? And the reason we did that is because, these guys were off by an index, but now that I've summed this up over all p's, these two guys are actually the same thing, right? And it turns out that this is what we call an exact couple. What does that mean? That means that that means that this guy and this guy are the same, and that this diagram is an exact sequence, right? So like the image of this is the kernel of this, etc., right? So this is what we call an exact couple, and I'll discuss this in the next slide. But basically, it turns out that an exact couple, from an exact couple of like of this type of things, you can actually form a spectral sequence, right? And now what's the Atiyah Hirzebruch spectral sequence? Well, you let xk be the k skeleton of my CW complex. So the filtration was just by the k skeletons. And then I take the spectral sequence corresponding to this exact couple, right? And that's the Atiyah Hirzebruch spectral sequence. And now if you look at this, so this is like the first page. If you look at the second page, the r equals 2, then it turns out that the terms are precisely these guys, which is what I promised at the beginning of the section, right? So this is like the spectral sequence. So now let's actually discuss like how the exact couples work, because I think that's interesting. So let's say I have an exact sorry, can you guys hear me? My computer kind of spammed out for a second.
Yeah, you just cut out for a second. I was worried it was me.
Yeah, all right. So, all right, so we have this exact couple, which is, as I defined before, this whole thing's an exact sequence. Now, what you can do from this is form what we call its derived exact couple. And what this is quite simply, it's quite simply this thing where you basically take the image of A, replace A by the image of A under I. So we have this. and then replace C by the homology of a, so it should be C with respect to D, where D was JK, right? So, JK is from C to C, right? And, the maps are like kind of the obvious ones you'd expect. So, this is what we call the derived couple of an exact couple. And, the derived couple of an exact couple is also an exact couple. So you can also call it a derived exact couple, if you will. And, this is a good exercise in diagram chasing. I highly recommend, pretty fun, right? So now we go to the last part of this talk. This is like the theorem, right? So let's say, you have this like exact couple of bi-graded abelian groups, right? Which is what we had, right? With our homologies. And let's say like, I has like degree -1, 1, J has degree 0, 0, and K has degree 1, 0, right? And now let's take like successive derived exact couples of this, right? So after the first step, you have C2, right? After you go to the derived couple of this, after the next, and then the next step, you have C3, etc., right? You take successive derived couples like that to get these objects after the R-1th derivative or derived couple. And it turns out that the objects downstairs in the derived couple alongside the maps JR, KR, just like going through this diagram, it turns out that this is a spectral sequence. Right, I have not included a proof of that here, but yeah, this is how we constructed the Atiyah-Hirzebruch spectral sequence above. And Hatcher also uses this to construct some other spectral sequence, like the Ceres spectral sequence. So this is a pretty useful general tool. And with that being said, that should be it. Any questions? All right, so that's the end of the talk then. Yeah. Oh yeah, Max, that should be the end of the talk, by the way.
Okay.
Yeah.
All right, let me stop the recording.